Hey guys, let's talk about solution stoichiometry. In this video, we're going to learn how to do stoichiometry, except this time you're going to be given different solutions along with the concentration. So you're going to be using what you've learned about molarity and everything you've learned about stoichiometry and combining those together. Okay? Now, you understand at this point, everything is predicated on a correctly written and balanced chemical equation. It's all about those mole ratios in that chemical equation. So we're going to jump right into this one. Example 1, here we have 50 milliliters of a sample of sodium hydroxide. We're given the molarity, we're given the concentration, and we're given the volume. And it reacts with an excess of magnesium chloride. All right, so that means we know sodium hydroxide is the limiting reactant. And we're being asked how many grams of a precipitate form. Okay. So we're going to need our solubility rules or solubility table or a working knowledge of the solubility rules and some of the facts that we've gone over repeatedly. You may not even need those sheets anymore. Okay, so first things first, we're going to go ahead and write and balance the equation. So pause the video and give it a shot, and I'm going to go through it right now, okay? Before I do that, I want you to determine which is a precipitate. So you know this is a double replacement reaction. And one of the products is sodium chloride. It's a group 1 metal, and those are always aqueous. So that's what I meant. If you remember that, then you know magnesium hydroxide should be the solid. And indeed, in the bottom corner, that's exactly right. Magnesium hydroxide will precipitate out of solution in this chemical reaction. Okay, so now we're ready to write and balance this reaction. Okay, and like we always do, we write down what we know. Well, we know we're being asked about how many grams forms here. And we know we have concentration and volume of the sodium hydroxide. And we know the definition of molarity is moles divided by a liter. If you rearrange that, molarity multiplied by volume equals moles. And we have to get this into moles. Once we get it into moles, then this becomes a straightforward mole-to-gram stoichiometry problem. So we're going to take what we know about molarity, rearrange it, we're going to plug in our numbers. We need to make sure everything is in the right units, and we have 50 milliliters. So what that means is, at this point, you should be able to just bump that decimal 3 to the left, okay? You can easily convert this into liters. If you still want to use dimensional analysis to do that so you don't make a careless mistake, perfectly fine with me. I'm going to go ahead and throw it in the equation and look at what's happened here. We have molarity times liters. Those units cancel out and give me moles of the sodium hydroxide. Now it's time for some dimensional analysis. So where do you start? Well, the only place you can. You start with moles of the sodium hydroxide, okay? So moving through our computation with moles of sodium hydroxide, we're going to use dimensional analysis here, and we have a 1:2 ratio going on here. That's our mole ratio. 1:2, factor out. Our connection always from mole to gram, molar mass. So for moles of magnesium hydroxide, in each mole there's 58.32 grams. That's it. No need to go any further in the land of the mole. Multiply everything on top, divide that quantity by everything on the bottom, and you'll get a final answer with 3 sig figs of 0.146 grams of the precipitate. All right, so moving on to the next one here, example 2. What mass of nickel wire reacts with all the silver nitrate in a 1.25 liter solution of concentration 0.15 molar? All right, so this one, we're being asked a question about the reactants, okay? All right, so we're saying we have this concentration and a volume, and we want this reaction theoretically to go to completion. Okay, so where do we start this one? You guessed it, a balanced chemical equation. Okay, this is a single replacement reaction. You can look at your activity series of metal. This reaction does occur, and as a result, we're going to yield nickel 2 nitrate in solution, and along with that we'll have our solid silver. Okay, so we're going to write down and look at what we are being asked for. So we're being asked for what mass of nickel wire, question mark grams, reacts with all the silver nitrate in this solution. So we want this reaction to go to completion. All right, so we're going to need to find moles here. Let's find moles here. And then once we find moles, this is a straightforward stoichiometry problem. All right, so we have volume, we have the concentration, which means we can easily find moles. Easily. So once we multiply this out, you can find the moles of the silver nitrate. Once you have silver nitrate, you are ready for dimensional analysis, and you're going to use that and stoichiometry to convert ultimately into how much is needed. So liters of silver nitrate, liters of silver nitrate. Look at this. I start with the volume, but I know in 1 liter of silver nitrate there's 0.15 moles. I'm told that in the problem. Okay, then I have my molar ratio here of a 1 to 2, 1 to 2. So using that allows me to convert from silver nitrate into the other reactant, which is nickel. And I know in 1 mole of nickel, there are 58.69 grams of nickel. And that's what I'm being asked. What mass of nickel? Okay, so go ahead and pop this in the calculator. Multiply everything on top, divide by everything on the bottom, and your answer with 2 significant figures is 5.5 grams of nickel. Okay, feeling good about it. Example 3. In this case here, we have 150 mils, and we have a sample of barium chloride of concentration 0.15 molar, and it's reacting with 55 milliliters of a 0.13 molar sodium sulfate. Oh no, we have 2 reactants, and we're not being told which is limiting. On top of all that, it's being given to us in concentrations of solutions, and we're being asked about a precipitate forming. Okay, first things first, stoichiometry, a balanced chemical equation, always. Okay, watch your nomenclature on this one. All right, both reactants are aqueous, and one product is solid. That's our precipitate, so that's the one we're being asked about, grams. And we are given information about both reactants. And this guy over here, just a spectator ion. It dissociates, okay? All right, so anyways, next thing we need to do is convert both reactants into moles, okay? Both of them, one at a time. Get them converted into moles. Starting with barium chloride, how many moles do we have? Well, we take the molarity multiplied by volume. Make sure your volume is in liters, and we get the moles of barium chloride. Let's do the same for sodium sulfate. Again, Make sure everything is in liters multiplied by the concentration, and we get moles of sodium sulfate. All right, now we're getting somewhere. Okay, now we can move in to some dimensional analysis and stoichiometry. Okay, now you may notice something about the molar ratio at this point. Good for you. I'm going to continue moving forward. So now I'm going to use stoichiometry to convert both of these quantities into grams of the precipitate. All right, so having done that with barium chloride to start off with, and if you don't see it, if you didn't see it then, you see it now, it's a 1-to-1 mole ratio, guys. And in 1 mole of barium sulfate, there's 233.39 grams, and we're being asked for grams. And when we go through and do the same thing for sodium sulfate, oh my goodness, really? It's a 1-to-1 ratio. So it should have been very obvious, simply by converting them to moles, that the sodium sulfate was going to be our limiting reactant. Having seen that initially, you could just do one line of stoichiometry and say, okay, the answer is 3.7 grams of barium sulfate. We cannot form any more of that. What about the barium chloride? It's an excess. It's left over like some slices of bread and meat, okay? So that's a really cool stoichiometry problem there. And so in this video, we have continued looking at the mole. We've continued looking at stoichiometry, and there's a problem set that'll give you all the practice you could imagine doing solution stoichiometry. I'll see you guys in class.